I'm Moses Guttmann. I'm the CTO and founder of Allegro AI. And today we'll talk about best practices in deep learning and the art of research management. This workshop was adapted to this online session. So we'll have the first part go through kind of a deck presenting the background, problem, etc. And then in the second stage, hopefully we will be able to do some hands-on and really see how to get going and get started. Not sure I can always see comments on the Slack channel, but I'll try to check from time to time. Please feel free to ask questions and interrupt in the middle, but hopefully I want to say it'll be a discussion. Hopefully it'll be half a monologue. So a bit about our company, founded in 2016, a few investors and partners, big names, about 30 something people. What we mostly do is we develop AI infrastructure, which is kind of an end-to-end solution to building your entire product on top of AI. So we build the infrastructure for you, regardless of the product that you're developing. A bit about what we will be talking about here today. So essentially, you can think of the problem of deep learning as kind of the 20-80 rule. So where 20% of the effort, some would say 10% of the effort, is basically getting a Git repository to work, running it once, getting things actually working, a model that actually detects something, and then most of the effort is put into understanding your data, rerunning models, debugging your code, debugging your models, etc. And the idea is, how do we make the 80% effort as automatic and as scalable as possible? Because a lot of the things that we do, we basically repeat the same processes over and over, and we want to automate this entire process in order to actually move faster, right? So that's kind of the idea. Obviously on the right, you can see myself, well, without the glasses, I guess. So, and that's kind of the idea. Most of the time, what we're doing is we're working on the data and the code instead of actually running models, and this talk is all about how do we very quickly move from one to the other. So it's all about actually what is kind of dubbed these days ML ops or DL ops, right? So you can think of it as a general way to say, okay, we just need automation. And this is not the standard production automation. This is a different kind of automation. And the reason why it's so complex is because we basically have to cater for 3 different personas in the organization. So we have to help the researchers, we have to help the engineering department, and at the end, we want to build an entire pipeline into production and then feedback data back into research and engineering, right? So the idea of the researchers is basically we want to make sure that we can write a piece of code very quickly, see if it's working, then pass it on to the engineering department where hopefully things will scale. So more data, testing various parameters, configurations, etc. And then in the end, we want to have that model, the output model, as part of production, but still be able to not only automate these processes, so think like continuous integration, etc., but also have a way to retrieve feedback from the actual usage of that specific model, and then hopefully reiterate this process. So over time, we'll end up with better and better models. So in order to achieve all that, we actually have to have seamless integration between one persona to the other, one stage to the other. Because every time we have a manual process, that means that we cannot automate it, that we cannot scale things, and we cannot parallelize the effort. So the idea here is, so how do we take a code that someone is writing on their own personal computer and make sure that everyone in the organization can reuse that same code. So I see, do I have a message here? Yeah, I'll share the link to the slides later after the talk. I'm not sure I can share all the slides, so basically we'll compile something and then upload everything to the GitHub alongside the code and everything else. The idea here is to basically, so I'm just making sure everyone can see my screen. Is that correct? No feedback, so I assume it's correct. Is it clear? Yeah, I'll assume yes. Okay, so let me just switch back. Okay, so basically, the idea is that we want to move code between different personas in the organization as quickly as possible without anyone needing to package software, code, environment, etc. So the stage one is the researcher. So the idea is that a data scientist will be able to write their own code on their machine and be able to expose meaningful insights within the code itself. So think of it as a set of arguments that we want to export, maybe parameters, maybe any other metrics or debugging information that we want to expose as part of the training process itself, and have that embedded in such a way that someone else can take that information and without exchanging any actual conversation, not that that's wrong, but it just doesn't scale, be able to rerun the entire training session and then use that as a baseline and continuously improve by changing the different parameters and getting the feedback from the different debug information or reported performance metrics. Then we have the engineering, that is basically, think of it as automation process and testing for the training of the models, right? So we want to take a model, like think of it as a baseline, and then sweep over all the different parameters of that model, try to run it against different data sets. So maybe it works well on a specific data set, but on another, well, not that good. All that information, want to package it and then send it back to the researchers, basically saying, here's where it failed, what can you do about it, right? And we want to have that entire thing in such a way that they'll be able to reproduce it and say, oh, we have an idea on how to do that. So that's kind of the first iteration between the researchers and the engineers, right? Then obviously we have production. So how do we think about production when it comes to deep learning or learning in general? So we have quality control. So how do we make sure that every time that we want to release a model, it is at least as good as the previous model, right? And we have to create an automation process for it, right? So in software, we have unit testing and doc testing and system testing. Basically, we can say, okay, just run that code base against all the different tests. Everything passes, we can release it. What do we do with models, right? So we have to take the model, run it against a blind data set, make sure that the performance is at least as good as the previous model. Then that actually will say that that model can pass to the next stage, right? And the next stage is, okay, so now we need to package this model. Basically, how do we containerize this entire environment that might change from one model version to the other? Because unfortunately, the frameworks are still constantly improving. This is still the beginning. So no one will freeze a version if the framework actually fixed a bug, where it's maybe faster or converged better or whatever it is. We need to make sure that we can do that as well. And then at the end, we want to be able to take that packaged model alongside all the environment, and we need to make sure that we can deploy that into whatever orchestration solution that we're using and within the organization. And then the last part is we have to make sure that there is a way to basically fetch data on the actual performance of the model. So think of it as insights on whether the model was correct or incorrect, right? Sometimes they're direct and sometimes they are indirect, right? So if the model in doing autonomous driving did something, and maybe the hands on the wheel changed location, or actually you put your hands on the wheel, that's an insight that something might be not as accurate as you thought it is, right? So that's an indirect feedback that we want to store alongside the entire data that the model is working on. So that entire feedback loop has to be integrated into the production of that model. Otherwise, we're flying blind. We have no feedback on how the model actually performs in real life, right? And then it means that we need to fetch data or create data sets manually instead of automatic. Okay, so with that in mind, the idea is to automatically create as much as possible and package everything that we can in such a way that everything can be passed from one stage to the other through a hub, basically containing or storing all the different data inputs of the training session. So that means that when we first execute the original code base, meaning on the researcher's machine, we want to make sure that we know everything about the environment that they are using in order to later reproduce it. We want to make sure that all the data sets that we're using are stored in such a way that everyone in the company can access them. Otherwise, the knowledge is being lost. And this entire idea of passing metadata alongside models and code is basically why experiment management is essential key in the solution for this end-to-end management platform, right? Because you have to have a hub that actually stores all the different inputs and data in order for you to move from one stage to the other. So these days, this is still an experiment manager because for most companies, we're still at the beginning. We're still doing a lot of research, engineering. There's not a lot of production. Over time, this will be switched to a different way of looking at things, maybe more of a DevOps solution. But right now, for a lot of companies, this hub is basically the experiment manager that actually stores how do we create the models and how do we manage them, how do we deploy them. And this is why we call that the experiment manager hub, right? That's kind of the idea. So with the experiment manager as a hub, let me just introduce what we did in Allegro AI. What we did is we open sourced basically our internal experiment manager and DevOps solution. We called it Trains. It's available on GitHub, later links, etc. This is essentially this hub that allows you to create everything and store everything and share this entire information when you want to move very quickly from the research to the engineering to the production, right? That is the infrastructure that allows you to do that and to automate this entire process. So the key here is basically to be able to do a very quick collaboration and automation. And the second one is the DevOps or the DevOps efforts. They need to be part of this entire effort of building better or training better models, right? We need their help in order to access the resources that we need in order to train models, because these GPU hungry resources, we need someone to manage them. And the idea is that we created a platform that is open source that helps with that, helps with not only the development, but also the management of the resources and the automation in order to actually get as quickly as possible from running your code on a single machine to running it on basically a set of machines or creating your own cluster. So what is this solution of train? So basically, it's what we dubbed Automagical Logger, which means you don't need to change your code. It's you literally just import a package and you initialize it. Everything else is done in the background, so monitoring your environment, storing everything that can be extracted from a single execution in order for later the agent or someone else to reproduce this entire environment and entire code base on another machine. This actually allows us to do automation and scale and sharing of code. That's the idea. The second is obviously the experiment manager as kind of as I mentioned before, the hub that connects everything. And obviously the version control that you can use, because at the end, we're training multiple models and we want to make sure that we can track what's going on, right? So the idea here is that just like version control that we have for software, we need to have a solution for model or deep learning or machine learning processes. And these are not linear processes. It's not a progression always, right? So what I have now might not be better than what I had 6 months ago, right? And we need to have that in mind when we think about the versioning of such models, right? So instead of kind of a very thin tree going up like we have in version control, this might be wider with many branches and many experiments that died along the way. That's kind of the idea. And obviously we want to have the DevOps built into this entire architecture so we can very quickly move from running an experiment on a single machine to scaling it to running it on multiple machines on the cloud, wherever. That's kind of the idea. So here's the kind of the idea behind it. Here's a 3 different steps that we'll try to cover with this workshop. Hopefully we will be able to. The first is a research. So how do we write code? How do we connect code with the system? How do we log what we're doing? The second is the engineering part, where we want to remotely execute the same code base. So take an experiment that we executed on a single machine and then execute it on a remote machine with a different set of parameters, arguments, etc. And then the last one is automation. So how do we automate this entire process? How do we automate data pipelines? How do we automate parameter search, etc.? That's the idea. So essentially, this is what we're doing with the client itself. So this is how it actually works. We add those specific 2 lines. So we are importing the trains package and we initialize it, right? That's it. The rest is done in the background for us and is done automatically. So we don't need to invest time and resources into the integration process. Otherwise, it will be very hard to do a lot of experimentations, and it's all about experimentations. That's what we're trying to help with, right? So what it will do, it will track the code itself. So tracking code means storing Git repository reference or a single file as a single script. It will log all our hyperparameters, so think R parser, etc. It will log all the model checkpoints, so we can actually reuse them and share them. It will log all the metrics and console outputs that we use, and obviously it will allow us to expand it with more and more information. That's the idea. So, and how it looks like. So basically it's a panel that you can see all your different experiments and who's running them, and you can compare them, and you can share them with other peers. And basically the idea is this is how you end up selecting your best performing model and debugging your current process. Once you store that, you have that, and you can move to another project. You think of it as kind of the engineering of a project. That might be another project taking that and automating this process, and then another project taking that and deploying everything else. And you have a single place where everything is stored, so you can go back, understand what went wrong, how to improve, etc. And at the end, obviously, what we want to be able to do is to have all that manual process automated, right? So we created a REST API and a Pythonic API to do just that, to automate the process of sending experiments for execution, to changing parameters, to comparing them, everything you can do from code. And the idea is that there is no need to create very complex YAML files or manage your own Kubernetes cluster. It's an option, but now it's not a must. And so how does it actually works? Basically, before we talked about the agent itself, so basically the Python package. Now there's an agent that connects a machine to the cluster, which means basically it's a daemon running on the machine, pulling jobs, setting up either virtual environment or a Docker, cloning the code, putting everything into that specific Docker environment, running the code itself, and reporting the progress. That's it. The idea is that it should not be very complicated to connect multiple machines and use them. There is no need to have a dedicated DevOps team just for the training machines that we're constantly using, right? So if you have one, then that's great. It can connect with Slurm or Kubernetes, but it's not a must. You can start small and then grow with basically the same set of capabilities. That's kind of the idea. And then obviously, once you start to automate things, you can actually do very interesting things like compare hyperparameters, create leaderboards, that kind of stuff. We'll try to cover that in the session if we get to. And obviously want to make sure that you create transparency in terms of cluster management. So we want to make sure that we can see all the different machines running, and we can see their performance, etc. First step is installing the train server. If you go to the GitHub page, which I'll do while we're talking, let's see if I can, where is it? And you go to the train server, then you have full instructions on how to install the server itself. So the server is actually running basically the web app and multiple databases, acting as the hub that connects everything. You have to have a server, right? So the idea is that you share information, and within the company or organization, then that server everyone connects to, right? So we'll start with setting up the server. Basically, you have two very simple choices. You can set it up with Amazon EC2 or Google GCP Compute Cloud. These are built-in pre-packaged images. Basically, click on the instructions and set them up. I'll demonstrate now how you can basically set up the Docker Compose on your own machine. This is quite easy. Just so you know how it works, it's not complicated. The idea is that you can either have it on-prem or on the cloud, whatever makes sense for your specific company. And then you can always move it later. If you have Kubernetes, there's also a Helm chart, which is literally just a single line to get up and running. So what we can do, so we basically get the Git repository, and we have Docker Compose, and we just need to pull the all the different Dockers, which I think are synced, so it should be just fine. Once the last one is synced. And then we need to create the folders, which I already did, but just so you know, there are a set of folders that you need to create. Basically, they'll store all the persistent data of your server. If you end up moving a server from like the cloud, on-prem, whatever, these will be the folders that you'll need to back up. You can have instructions are here. Basically, that's the setup of all the different folders, right? So just make sure that you remember to create them. People tend to forget, so that's important. We already have them. So, so we have all the different folders, and the only thing that we need to do is basically to spin the Docker up. Once that Docker is up and running, which will be in a second, hopefully up and running. And now we can switch to the browser and go to our server, and that's it. Our server is up and running. I can connect to it. So notice that by default, the server will allow anyone to log in. This is by design, so it's quite easy to use within the company itself. If you want to limit users, have username, password, look into the installation guide. There's an entire section on how to configure it. It's basically just setting up a JSON file with all the different username and passwords. So once we have that ready, basically what we need is to actually install the package itself, which let me just switch to another bash here. And so what we need is, let's go to the events folder. So what we need is to just install the package. That's it. That's pip install. And then we need to configure it. So we need to call trains init. And now we need to copy paste the credentials. Now, this is important. This is how the system identifies you, right? So the credentials files that is stored on your machine will identify you throughout the entire lifetime of the trains session, right? So wherever I go, if I'm using my own machine, I will always be using that same set of credentials. I can share them with someone else, basically copy paste the entire file itself, and they will hold everything that I need in order to log in. There's no need to add anything in your code. The idea is that I can run my code and someone else can run the same code base with the same connection, but with a different user, right? That's kind of the idea. So how do I create the users? I go to the web page, and then I just need to create a new user set. Basically what I'll do here is, instead of running it on my machine, I want to run it on the demo server that we have set up for everyone to use, basically to experience trains very quickly without even setting up their own server. So I'll be using that, and you'll be able to see everything that I do on the demo server. So you can actually do that together. So we can go to the demo op server and log in. So let's say, so now I'm logged in. So I can go to that profile page and just create a new set of credentials. What we have here, the access key and the secret key, these will identify us, right? So we can log in from the web, but everything else that is done is authenticated with those two keys. Now what we need is just to copy paste them. So It will tell me yes, yes, and we're all set. So now we have configuration file and it's authenticated, and that's it. So let's go back here. So we install the server and we set up the client itself. So the client is configured and accessed, and we can access it. Now let's see some examples. So we have like 30 minutes or so. And then we'll try to automate things. So let's switch to the PyCharm session. So let's start with something very simple. So this is a Keras example. I think that's basically straight out of the Keras sample folder. You can find the code itself on the GitHub. So we created a GitHub for just this event. You can go here. Where is it? We don't need that any longer. So there's events, and you can just see the entire code. It's right over here, so you can run through it now. So what we added to this code is basically this line. That's it, right? So we imported the trains package, and we initialized it with the project name and the task name. So task is, think of it as a general purpose experiment, right? Because we will be later using tasks for other things. And right now, a task, you can think of it as a single experiment. So the name of the task is not a unique identifier. I can have multiple tasks with the same name, and I can actually rename them later in the user interface, right? So that's the identifier of a task is actually the ID, which is a unique ID throughout the entire system. So let's run this experiment. So it's this one. So what it's doing now, it's connecting to the demo server, and that's it, creating a new task, and the rest is basically the same. So hopefully it'll be able to connect with the demo server. So it created a new task, and here's a link to our currently running task. So you guys can see it as well. So everything that is printed to the screen we will see it in the web app itself, regardless of where the machine is located. So I can monitor what's going on from a remote location just by using the package itself, which is very convenient when you want to track your machine at the office while you're at work, while you're at home, for example. So if we go back here, so that's a project that we created, and that's the experiment. You can see it here. We can also see the actual code that is running. So this is a link to the actual Git repository storing our code. That's a commit ID of the actual code that we're running on PyCharm. That's a working directory, obviously. If we change the code and we forgot to commit it, no worries. All the uncommitted changes are stored and then later reproduced on another machine, right? So that's the idea. The idea is that I don't need to worry about how to reproduce my code. Someone else will take care of that, right? And with that in mind, so the second stage is, so all the different Python packages that my code actually uses. So that's not an entire pip freeze of the entire Python environment. That's actually what I'm using when I'm running this code, right? So it actually dives into the code itself and only logs the packages that I'm using, not the entire rich environment, because that sometimes will be very hard to reproduce. That's actually what I'm using, right? And then there's details of actually who's using that specific package, etc., which is always fun to look at. We have the hyperparameters. So this is Keras, so it's using TensorFlow. So all the TF defines are automatically logged. It also uses some arg parser, so we can see the different default arguments, or maybe arguments that we used in that specific run, so the batch size, the number of epochs. We can see the artifacts. So the artifacts, we can store here any artifact that we want to create manually or automatically. All the models that were loaded or stored within the code itself will be automatically logged here, right? So I can see the specific model. This is the input model, which means I loaded the weights from that specific model. And that's the output model. If I click on the model name, I'll get to the model page. So I can see where the model is stored. So that's an actual link to where the model is. Notice that it's local. We'll deal with that later on. We have all the previous versions of that specific model. So we know we actually created 6 models that are stored basically in the same place. And obviously, we can go and look into the logs themselves. We can see different graphs. So those graphs are graphs that were reported to TensorFlow, to TensorBoard, right? So everything that is reported to TensorBoard is automatically cached while the code is running. So not post execution, but while we're executing the code itself. And we can see it on the server, right? So you still have your TensorBoard file, which is very convenient when you want to dive into the debug networks, understand the layout, etc. But if you want kind of broader picture, just understand what's going on, then everything is logged, and you don't need to worry about deleting files, etc. Last nice thing that we have here is monitoring the machine resources. That is done in the background for us, so we know the CPU temperature and utilization. And if we were to have GPU as well, then all the GPU statistics would have been here as well. Plots are basically any scatter or non-time series data that we want to store. So things like ROC curves or maybe activation, etc. So these are the activation that usually are stored in TensorBoard, only visualized as a 3D surface here. So you can scroll down, you can see them all, which is very pretty, but kind of useless, but it's still nice. And debug images, just a way to expand. So think of it as like images or audio that you usually store with TensorBoard. So, so this is what we had here. So essentially the same thing. Let me just check if we have some questions. Okay. Oh, questions. Okay, so let me see if we can zoom in here. So as you can see here, the only thing that we added, right? I just want to make that clear, is that line, right? Everything else is done in the background for us. That's the idea. So that's, with that in mind, let's try to find something else. So maybe torch. So that's PyTorch, same thing, same idea. So right now we have, if you're working with Torch or Keras or TensorFlow or scikit-learn with JobLib or Matplotlib, everything will be logged for you automatically. If you're working with MXNet, please create an issue on GitHub, and then we'll know someone is actually using that, and we'll add that as well, right? But that's actually what we are currently supporting. Some other stuff is on the way. Same here, same thing here. So we imported the package and we initialized it probably here. Okay. So as you can see here, let me just start the execution. So this is PyTorch using TensorBoard as a way to visualize data. You can also visualize data directly with the trains package. So there's a nice interface to send scatter data and time series and confusion matrices and whatnot. That said, when you start, especially when you start on a new repository, the easiest way is to just make sure that everything that repository is doing is logged. Then you can always add on top of it more and more information, more and more debug from outside of the model, outside of the code, so you can have a better view of how that actual model is behaving, right? Probably one of the most important things is to actually have some sort of a visualization on what's going on, what the model is actually training on, etc. Catching very quickly bugs in the code itself. So what we're seeing here is that's the arg parser that this model, this code base is using. Same thing here. This is a PyTorch example straight out of the PyTorch repository. If we go back here, can we tag or bookmark experiments? Oh, that's a terrific question. So let's assume that I have this experiment, and I have this experiment actually that is running, and I want to say, hey Cav, take a look. This is really interesting. You can press on the share button, copy a link, email it to you, and then what you'll do is basically open that link, and you'll end up with the exact same page open on that same tab for that same specific experiment. Actually, you can, let me just move it here, you can actually have like a close-up look into all the different plots here. Obviously interactive, so you can zoom in, zoom out, you can store them. We just added log scale because it made sense, and download the data and store PNGs of it, etc. That's obviously being updated in real time, as you just saw. It's just reloaded, and obviously we can turn off a few if we don't like them because it's too confusing. Over here, hopefully, yeah. So we have a few images. So I can see that I have iteration number 100 and then 0. I can actually go back in time and see previous iterations. And I can see the images themselves. So that one is 9, I guess. I don't know, maybe 9-ish. So that's just a way to demonstrate that we can actually send data alongside the experience, which is very important because now I can basically tell someone, hey, take a look here. For some reason, it outputs 9 here and what is it, like 4 here. Maybe it's right, I don't know. Anyhow, the idea is that I can very quickly share that information with someone else and say, hey, I think we might have a problem, or maybe I want to share this specific plot and say, hey, our performance is quite good, or whatever. In the meantime, we can dive into what we can do with an experiment. So an experiment, so first of all, we can change the name of the experiment. This is obviously the best one. So we just change the name, that's fine. It is meaningless. It's just, it helps us understand what actually works best and add some comments. That's the ID. If we click on the ID itself, that's the actual identifier of that experiment. That will stay the same regardless of everything else. So we can move experiment to different projects, different folders. That ID is consistent. Obviously, we can search through experiments. So that's basically a way to filter out results. We can also, so let's clear that. We can also, and that's important, people actually miss that, we can actually edit the description. So we can say something here, and we just added something in the description, so I can actually copy paste some whatever I need in order to better describe what I did here, or what worked, or maybe leave a note for someone else to read later. That is actually quite useful. And then obviously I can search through it. So if I write something, I'll only get the experiment that actually stores that. We can also see the different columns. So I can sort by updated time, but I can also add maybe a metric. So we have the loss, and loss, we want the minimum value. The maximum value is not very important. And maybe we want to add some hyperparameter. So what was it? learning rate. Okay, so now we have two more columns. We can sort by them. So we have the loss, the minimum loss, and we also have the learning rate. And we can basically create this leaderboard where we have the best performing models, or we can better compare and understand what works. I was able to get everything logged on my experiment just by adding those 2 lines of code, which is as seamless as possible when it comes to code, right? I only needed to install the package and that's it. Whatever I do now, I add those 2 lines of code, I have everything here. The seamless part is when I'm able to clone this experiment. I'll demonstrate now, and then hopefully we'll have time to actually set everything up. When I'm able to clone the experiment, which means that I'm cloning the environment and the parameters. So I have a copy of the experiment. It points to exactly where I was before. Now I can change parameters. So let's change the learning rate. Where was it? So, and I can put it into an execution queue. And now it's pending for execution. And now another machine can connect to it, and which I'll demonstrate in a second, and pull that entire environment without me doing anything. That's seamless. That means that someone else can rerun my code on another machine or their machine without actually talking to me. So they have all the information they need. They can change parameters. They can read my documentation, and I never had to package the entire thing into something that they can run. Someone else takes care of that. Actually, it's not only just running a machine, they can actually restore the entire environment so they can work on the code itself, basically with the help of the trains agent as well. So basically you can build an entire environment instead of running it. If we have time, we'll touch that as well. I want to explain something about running code. So every time that we run the code, if that code never produced something that the system thinks is valuable, it will try to reuse the previous experiment, which means if we are just debugging stuff and we never actually created a model or an artifact, by default, the system will reuse the same experiment. So overwrite the same experiment. Obviously, this is configurable from code, so you can say never do that. The idea is that it's a way to mitigate the clutter of just every execution, another line in the table. It's whatever you can decide on whatever way that makes more sense to you. I just want to point that out because for some people it's very confusing, and for others it's very intuitive on why and how it works. So bear that in mind. Okay, so we have the current experiment that is running. Basically, we re-executed the same code again, and since the original one, we actually changed the name, or a model was created, so it created a new experiment, and now we can compare the two. So let's just do that. So let's select the 2 experiments, and now we can compare them. So comparison. So first of all, we have a table of summary, so we can compare multiple experiments. Obviously, I'm just comparing 2. So we can see that the model is actually using the same input model, exactly the same one, which is nice. So I know it's the difference is not from different initial weights. I can see that it produced another model file, which makes sense, but I can see that everything else is the same. So that's the same source code, same install packages, everything is the same. Now we can go to the hyperparameter section. We can basically see if something changed. No, it's basically the same. If something changed, it'll be red. We can also do some cool stuff. We can do some parallel coordinates. So I can say, you know what is actually makes sense to me is I want to compare the loss and then see if there's learning rate had any effect, and maybe the seed number. And now I can, so it was the same. So obviously I got the same loss, but that's a way to dive into different parameters and their effect when we're comparing results. So if we have time, I'll rerun the same thing with a different set of parameters. And obviously, we can see performance. So let's just see here. So that's essentially the same, exactly the same numbers. Makes sense. That's there is no randomness here. So we can dive into it. I can change colors. That's the most beloved feature that we added, changing colors. Don't ask me why. Extremely popular. So, and then plots, if we have any, and debug images, same thing. We want to compare the 9 here and the 9 here, so we can. That's a way to compare different experiments and their performance and better understand what's working and what's changed. Mostly it'll be code, and then we can switch to the GitHub in order to change to see the changes between one version to the other. Okay, so we covered that. Let's see. So we have 30 more minutes for the session. Let's see what we can do. So TensorFlow, same thing, I guess. Let's just run it so I have something. No, and so the same thing works for TensorFlow. Not very interesting. I actually want to rerun this one with a different learning rate. So let's change the default to something else. Just so we'll have some nice comparison. And then that will actually demonstrate how the uncommitted code is actually being logged as well. So let's do that. So here's a new experiment, and we can see that we have uncommitted changes. That's exactly what we changed, the default parameters, so from 0.01 to 0.04. And we can also see that it's here, it's 0.04. We can also compare it, so now, yeah, and yes, the best. So we can see the output model is different. The execution has the same baseline, but uncommitted changes, we have something different. So it's red, so we know. But hyperparameters, where are they? So now we see we have different learning rate and still now no test loss. So let's just go back to the table just so we know. So here's the baseline, that's 0.04. Those are 0.1, so it's very easy to see that we have a difference here. Let's see if we can. It's still running. I want to see if we train, so loss in a second. So we can see the plots here. The scholars, sorry. These are updated live. Oh, and we can see that the train loss is actually converging faster, which is nice because we increase the learning rate. That's perfect. So if we wanted to go into the hyperparameters and see the effect of it, and then we can switch to the parallel coordinate and see that there is an effect to it. Hopefully it'll end soon, so we'll be able to see the test loss in a second. So that's kind of the idea of comparing different executions and diving into what actually caused the change in performance. Okay, so with that in mind, is it done? Yeah. Yes, completed. So now I'll be able to see that. Just refresh it. Hopefully we have it everything. So loss. And yeah. And okay, so and obviously we can sort it by our different columns here. So, and maybe add the, what was it? Test loss minimum. Makes sense. And you can see that's a test loss meaning, which obviously is the same for them all. Okay, so we had that. Now I would like to demonstrate. So yeah, let's see if we can get things going. Okay, so with that in mind, let's jump. So we covered everything secondary, and we'll cover in a second. We covered most of what we did here. Leaderboard is just a way to create those tables that are constantly refreshed. So you can maybe put it on a large TV screen, understand how a project is, like they perform a specific project, specific model, so you know where you're at, and then etc. It's just a way to filter things and understand how to beat them, or if we were able to. One last thing that I'd like to show you is that let's assume that this one was the best performing one. We can always mark it as publish, which means no one will be able to ever change it, because these, so let me just, we can always reset an experiment, basically forget everything. But if a model or an experiment is published, it means that no one can touch it. That's stored forever, and we can actually filter by a specific state. So we can say, oh, just give me everything that is published. Now we can see all the different performance of everything that is published. It's very convenient when we're moving into production or second stage, where we want to say, okay, just mark this one. This is the baseline that we will be able to compare against later on. Obviously, everything can be queried from code, so I can automate this process, right? So I can say, give me all the different experiments or models that are published as well. And the same can be done on a specific model, right? So I can say this model that was done automatically was published. It means that someone can use it in the system. And in a second, I'll demonstrate how that is done. But before that, let's dive into what we can actually do with data pipelines. So the idea of a data pipeline is, so before I dive into that, let's see if we have more questions. No, okay, good. So a data pipeline. So up until now, the assumption was I executed my code and the code produced a model, and I am able to reproduce the entire environment and said model on another machine, which is nice, and we'll demonstrate in a second how. But we totally ignored the data aspect, right? So how do I actually train the model? And in a lot of cases, the data is local, which means I have it on my machine. So now we'll talk about how to create data ingestion pipelines where we take the data, we actually put it somewhere. It can be on the trains backend, but it can support any objects storage as well. So think S3, Google Storage, Azure Storage, everything is supported. And then how do we get back the data, process it, put it back, create versions of the data set, and then obviously train with that specific data set in mind, where when we get to that place, that means that we're actually not tied to a specific machine. And that's the target, right? The target is I'm able to train on my machine. I can tell you, hey, that's the code, just run it, and you're able to do the same thing without me doing a single thing, right? So that's the idea. So what we have here, so this is a very simple piece of code. Let me just see. Okay, so this is what we have here. Basically, we created a new task. We created an artifact for the task. So now that's not an experiment, that's just a task, right? We created a new task. We upload an artifact to that specific task. So by default, artifacts are uploaded to the file server that is part of the train server. You can actually tell it to upload it to anywhere else. It's basically, if you look at the configuration file, there's the file server section. Whatever you put there will be the default of where you upload your data. We can, if we have time later, I'll demonstrate how you can do it via code, which is doable, but it's harder to conform. So everyone is using the same the same storage solution. So over here, the default will be the file server. So just so you guys see, basically, if we do this, so you can see that that's the file server, right? So that's where all our artifacts will be stored automatically. If we were to change it to S3 colon / bucket name, basically everything will be done there. Credentials at the bottom, you can add credentials, etc. So that's kind of the idea. So what we're doing here is we're taking this artifact object. It can be an object or it can be a local file, and we upload it. That's it. So let's just run this piece of code and see what we get. So, and that's basically the engineering department report. So think of it as kind of so there's this title, data engineer. That's the first step, right? So let's start by taking the data, packaging the data itself, the data set itself, and putting it somewhere. When data is more complicated, then sometimes it's a different way to package it, but it's the same idea. I don't want my data to be stored in a single machine. I want my data set to be shareable among people, and I want to have the data set versioned. And the idea is that a data set versioned is not the same as code version. So we don't want the data, the Pico file, to be part of the Git repository, even though it is doable with Git LFS. That is just not the right solution. We want to, at the end, it's a file. So we need to have file storage solution storing it. What we're missing and someone pointing, that's the data set. That's where it is. And that's exactly what we did now. So we put the file somewhere, and then we have an experiment pointing to that specific file. So this is how it looks like. So if we go here, and yeah, so let's sort by updated time, so it makes more sense. So that's the dataset artifact that we just created. So there is no repository. So what happened is the entire code was uploaded. That's a way to track what you're doing if you're not using any version control for your code. We also have the different packages used in the code. No hyperparameters, but we have artifacts. And the artifact is the data file itself. So this is the data file. I know nothing about it. So there is no preview because it's generally just a file. And this is a link to the file. If I click on it, I'll be able to download the file itself, right? That's the idea. But we don't just want to be able to download the file. We want to be able to access it through code so I can do some stuff to the data. So let's do that. So the second stage, so first stage, let's upload data somewhere. In this case, the train server. It could be just a shared folder as well, as long as no one will delete it from that specific point. The idea is that I have, I can track what I'm using, and then I can have that data fetched to me as quickly as possible without me doing anything. We created the dataset artifact here. Let's see, what's the name of the ID? Okay, so that's the name of the ID. That's the experiment ID, but now will be the dataset ID. So let's mark it so we know, okay, that's important. Let's publish it. Because this is important, it contains our dataset. And now we can go to the processing of the dataset. So the processing of the dataset, let's just use that. We put the dataset task ID, which means that's the identifier, that's the unique identifier that will help us get the original data. This is how we add a dictionary of parameters to the task itself. So if we're not using argparser or tf-defines, then we still want to add some arguments logged in the system, and later we can override those arguments. That's kind of key here. We use that dictionary and we connect it with a task. The reason it's connected and not logged, because later when you have an agent running, we will be able to re-execute this entire code base while overriding those parameters. And I'll demonstrate that. So we have 15 minutes. Yeah, I think we'll get there. That's important. So these are the arguments. Then what I'm doing here is I'm saying, okay, give me the original task. Here's the original task. And then give me all the artifacts. The artifacts are just a dictionary with objects. Any object is an artifact. And then we just say, just give me the original data. Get me a local copy of that artifact, which is important because it means that someone will be in charge of fetching the data, whether S3, shared folder, HTTP link, whatever, it will fetch it for me. More than that, it's cached. So if I'm re-executing the same program twice, it will not re-download the entire thing. It will just use the internal cache. And then I'm processing the data over here. We'll basically splitting the data, test and train. And then we're uploading the data back. So now we have a new data set. So let's run this code. So process data set. We're creating a new repository. It's saying you don't have code repository. We'll just copy the code. And these are the arguments. And now we're uploading back the newly created data set, and we're done. Okay, now we go back here. And this is the experiment that we just executed. So that's the entire code base, the different packages. So now we have sklearn, and we can now see the different hyperparameters and the artifact. So now we can see, oh, here are just the NumPy arrays that we stored. They're accessible as well, so I can download them. So it's NPZ. Nice, I can see what I have. Obviously here, that's a preview. So if the NumPy array is very small, you'll see all the numbers. If it's very big, it's basically the same thing as just casting to a string and then just a summary of what you'll have there. And obviously what we want to do is the last thing is let's try to train something based on that. So we open a notebook. So I'm just demonstrating a few other ways of interacting with the system. It doesn't have to be a notebook. Just it supports notebooks, supports Colab notebooks, Amazon SageMaker, Azure. I don't know how they call their notebooks. Azure notebooks, whatever they call them. Basically, same idea. We import the trains package. We initialize. We initialize here the task itself. Now we have an argument saying the task ID, which contains the data set. So let's take the correct one. So that's a task ID that we want to have. So save that. So, and we'll just retrieve the data. So watch closely. So this will get us the task object. So that's a data set task. And here we say, give me the artifact and just get me the object itself. If the system knows what that object is, which these days we support pandas, NumPy arrays, and payload images. All the rest are just general purpose objects as files, etc., or zip files or whatever. But if it's one of those three, basically get will give you an object. So you don't actually need to open the file and read it. Someone does that for you. Again, everything is cached. If it's not supported, you'll end up with just a string of where you can find that copy, local copy of that artifact. So again, here, that's a NumPy array. So we just get the NumPy arrays and then we train a logistic regression based on it. That's the iris data set. It's very trivial. And then we just plot. So let's just run the entire thing. So run all. So it will import the task, create a new task. So obviously, if we switch here, we will be able to see the new task. So that's a new task. So the new task already contains the code itself. So what it does in the background is it converts a Jupyter Notebook into code, right? So instead of versioning the Jupyter Notebook with all the outputs, it will basically version only the code itself. This is important because what we'll do next is we'll set up a machine and send that code for execution on a remote machine from a Jupyter notebook. All right, so we don't actually need to version the entire notebook. We need to version the code itself. So this is the code itself of the notebook. Again, same thing. So different parameters or different packages that we're using. For some reason, it thinks the sklearn version is 0. We can later edit that as well. We have hyperparameters. So that's the hyperparameter that we did. So that's the task ID. And we can actually log the results. So see that the model was trained. We can see the output model. So we created a new model. And we can also get the plot itself, which is exactly what we have here as a static plot. So what it did is it took the matplotlib that was created inside the Jupyter notebook and extracted that to the backend. So not only we have the plot here, we also have it on the backend, so we can later compare and dive into the details. And that's essentially taking code from one machine and executing it and using that code base on another machine. So with that in mind, oh, I can see someone is already running the code. That's awesome. You see, yeah. So that's really nice. Okay, so let's just do this thing. So what we can do. So with that in mind, so we have 7 more. Okay, so we'll run through it. So the idea now is how do we set up a machine and send everything for that machine to be executed? So let's see if we can do that. Okay, so now we're back in a machine here. So let's see. So never do what I'm doing now because I'll be connecting to the demo server. And generally speaking, you should connect it to your own machine. So what do we need to do in order to actually set up a machine and connect it to the cluster itself? Okay, so let's start with what is a cluster, and we'll run it very quickly, and then we'll end up in time. What is a cluster? A cluster is just a set of machines that you can control remotely. That's it. It's not multiple machines training for the same experiment. Forget about that. That's for another session. Right now, it's a single machine doing a single experiment. What is a job? A job is a single experiment, as we saw, that we clone and run. So think of it as basically a single line on the table. That is a job. How do we send jobs for execution? Basically, we put them in an execution queue, which is just a list of IDs of jobs to be executed. And then an agent pulls from that specific list, set up the entire environment based on that, on the data that is stored with the experiment, and launch the code itself. And then obviously the last one is, so once we have that, we can start to automate and do some hyperparameter sweeping, optimization, whatever. Okay, so how do we do that? So we do pip install trains agent, which is the agent itself, written in Python, all open source. You can check it out. Then we do trains agent init, which will ask for credentials, etc. If you give it nothing, it will automatically connect with the demo server. Make sure that you know that. I don't know what happened. Wait, let me just see if we have something, someone saying. The session will be, okay, short survey, okay. Let's do, so we have a few more minutes. Let's do that very quickly. So, so this is how we start the agent itself. We started on a specific queue. A queue is just, as I mentioned before, a list of jobs. It will run, this setup will run inside a Docker. So what we're doing now is, let me just switch here. And then you can see your machine here. Now it's connected. So I can see Dan's machine with the single GPU. And I can see that it's listening on a specific queue. It can actually listen to multiple queues. And what I can do is I can take my experiment here. I can clone this experiment. I can go to the execution, see that everything is okay. Definitely, I want to edit that. I'm not sure what it said, 0, but who cares? I can add it. I can actually edit the code itself. I can add repository, whatever I think is best. I can add the hyperparameter here. Let's do something that is completely wrong. So let's do 1, 2, 3. The idea is that I want to demonstrate how I can change the data set, the parameters, without changing the code. And then let's send it for execution on the examples queues. So now what will happen is this machine will fetch it and start executing the code itself. Okay, so now it started executing the code. So by default, it will be executing it on an NVIDIA CUDA Docker file, a Docker image. Everything is updated here automatically, so we can see that it's running on NVIDIA CUDA. What it will do is it will set up an entire environment on the inside the Docker, including the code itself, packages, etc., and then it will execute our code. So now it's setting everything up. Once it's done, we'll have everything here updated. So we'll have the entire set of packages, not only the ones that we're using directly, but the ones that we are also using indirectly. So we can reproduce the entire environment, and then it will basically run the code again with a different set of parameters because we changed them here. So the idea is that all the parameters that we see in the hyperparameter tab can be overridden from outside of the code, which is a very powerful tool because it allows to very quickly just add dictionary parameters even within the code itself. This is on purpose to fail. Because we want to be able to control the code without creating a very elaborate set of interfaces. So as you can see here, we try to fetch a data set with an incorrect ID, and it failed because obviously there is no such experiment. But now let's take the right experiment. So that's the right one, right? So no, that's the right one. So now what we can do is we can take this failed experiment. I don't like the red. Let's reset the experiment. Basically, we deleted everything. Can go back to the data set. Now we can put the correct one. And we can send it for execution. And it will start running again. So with that in mind, I have 1 more minute. Let's see what I forgot. Yeah, well, basically just go to the GitHub, enjoy. There's a Slack channel. Feel free to ask questions. Everything is on the GitHub. You can start using it today. That's it, I guess. I'm out of time. Last thing is maybe it's running. It's doing something. As you can see, just one last thing, everything is updated. So we have all the different versions of all the packages we're using in that specific setup. So we know that we can reproduce this entire environment on another machine. And with that, I say thank you and try to end this session on time. Is that okay, Joe? Are we good?
Yes, thank you very much, Mr. Guttmann, for your presentation. And we are also grateful to those who have attended this session. I'm going to go ahead and close the webinar now, and the survey will be served to you all promptly. Thank you, and have a nice evening.
Thanks. Bye.